Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 14-2. Damping modification for seismic force. In the previous lecture, we talked about damping modification for spectrum. How the design spectrum is modified for damping ratio other than 5%. And in this lecture, we will talk about how the seismic force is modified for the damping ratio other than 5%. And the seismic force including design basis seismic force, maximum considered seismic force, small to moderate seismic force. And here are some terminology. Damping modification for design basis seismic force. In Chinese, 设计基准地震力之阻尼修正。Damping modification for maximum considered seismic force 最大考量地震力之阻尼修正 Damping modification for small to moderate seismic force 中小度地震力之阻尼修正 Damping modification for design seismic force 设计地震力之阻尼修正 From the three forces, we take the maximum one to be the design seismic force. According to Seismic Design Codes Table 3.1, then we have the damping modification factor for design spectrum. And BS is the damping modification factor for short period structure. And B1 is the damping modification factor for 1 second period structure. When the damping ratio is 5%, there will be no modification. BS equal to 1. B1 equal to 1. When the damping ratio becomes higher and higher, the two damping modification factors also becomes larger and larger. If the damping ratio is other than those stated here, we may use linear interpolation to find the values of BS and B1. For example, if the damping ratio lies between 5% and 10%, then we can use linear interpolation to find the corresponding values of BS and B1. The larger the damping ratio, the larger the damping modification factors, BS and B1. And back to the example, the site locates at Yuishui Township, Hualien County, with supplemental dampers. The damping ratio of the building is increased to 8%. The question is to find damping modification factors for short period structures and for 1 second period structure. That is to find the values for BS and B1. From the Seismic Design Codes Table 3.1, we have the damping modification factors for damping ratio 5% and 10%. When damping ratio equal to 5%, BS equal to 1, B1 equal to 1. When the damping ratio is equal to 10%, BS equal to 1.33 and B1 equal to 1.25. Then we use linear interpolation to find the corresponding values for the damping ratio 8%. BS equal to 1.00 plus A minus 5 divided by 10 minus 5 times 1.33 minus 1.00 equal to 1.198. And B1 equal to 1.00 plus A minus 5 divided by 10 minus 5, 1.25 minus 1.00 equal to 1.150. So that we can have the damping modification factors for the structure with damping ratio 8%. Then according to the Seismic Design Codes Table 3-2, If the damping ratio is other than 5%, then we can have the design basis spectral acceleration as AD for site class 1, 2, or 3. And the spectral acceleration is modified by BS and B1. With these two modification factors, SDS is changed to SDS divided by BS, and SD1 is modified to be SD1 minus SD1 divided by B1. And the corner period between short period and medium to long period, T0D, is replaced by T0 parenthesis D equal to SD1 times BS divided by SDS B1. And according to T0 parenthesis D, then we can divide the relationship between SAD and T into 4 segments. The first segment from structural period 0 to 0.2 T parenthesis D, it increases linearly from 0.4 SDS to SDS divided by BS. In the second segment, SAD is constant and equal to SDS divided by BS. In the third segment, the spectral acceleration decreases and inversely proportional to the structural vibration period T, equal to SD1 divided by B1 T. In the fourth segment is the lower bound for the spectral acceleration, equal to 0.4 SDS divided by BS. And then back to the example, the site located at Yueshui Township, Hualien County, with supplemental dampers. The damping ratio of the building is increased to 8%. And the question is to find design basis spectral acceleration SAD. That's to find the value for SAD. And from previous lecture, we have some information about the building. SDS equal to 1.136, SD1 equal to 0.711, and BS from the previous slides, we have BS equal to 1.198 and B1 equal to 1.150. And the structural vibration period of the building equal to 0.268 seconds. And from the seismic design codes table 3-2, we can compute the corner period T0 parenthesis D equal to SD1 times BS divided by SDS B1. And after the computation, we have the corner period T0 parenthesis D equal to 0.652. Compared to the one with 5% damping ratio, 5%, T0D equal to 0.626 seconds. Therefore, when the damping ratio is higher, the corner period becomes larger. Since the structural vibration period equal to 0.268 seconds, it lies between 0.2 T0 parenthesis D to T0 parenthesis D. Therefore, according to the seismic design codes table 3-2, SAD equal to SDS divided by BS equal to 1.136 divided by BS 1.198 equal to 0.948. From the previous lectures, we have the information about SAD for the damping ratio equal to 5%, equal to 1.136, and compare these two, and we found out that the spectral acceleration, the design basis spectral acceleration for the damping ratio 8% is less than that for the damping ratio with 5%. If the site is located at Taipei Basin, the design basis spectral acceleration is modified by BS and B1 if the damping ratio is different from 5% according to seismic design codes table 3-3. And after the modification, SDS is replaced by SDS divided by BS, and the corner period is replaced by T0D BS divided by B1. With the corner period T0 parenthesis D, the relationship between SAD, spectral acceleration, design basis spectral acceleration, and the structural vibration period is divided into 4 segments. The first segment it increases linearly with the structural vibration period T. In the second segment is a constant. The design basis special acceleration is constant. In the third segment, the design basis special acceleration inversely proportional to the structural vibration period T. In the fourth segment is the lower bound for the spectral acceleration equal to 0.4 SDS divided by BS. Then we move to design basis seismic force reduction factor FU. Then according to seismic design code equation 2-15, FU, the design basis seismic force, can be determined by T, the fundamental vibration period of the building, RA, the allowable ductility capacity of the building, and T0 parenthesis D equal to SD1 divided by SD1 times BS divided by SDS B1. And then with this corner period, the relationship can be divided into 4 segments. The first segment it increases linearly with the structural vibration period from 1 to square root of 2RA minus 1. In the second segment, FU is constant equal to square root of 2RA minus 1. In the third segment, it increases linearly with the structural vibration period T again. And in the fourth segment, there's the upper bound, FU equal to RA. And then back to the example. And the question is to find design basis seismic force reduction factor FU. What's the value for FU? Okay, from previous lectures, we have already had the structural vibration period T equal to 0.268 seconds. And the structural vibration period lies between 0.2 T0 parenthesis D to 0.6 T0 parenthesis D. Then according to the seismic design code equation 2-15, FU equal to square root 2RA minus 1. And RA from previous lecture, we have already got this information. RA equal to 3.533. Then we can compute FU, the seismic force reduction factor FU equal to 2.463. And then compare with the FU, the seismic reduction factor for damping ratio equal to 5%. And then compare these two, we find that the seismic force reduction factor for damping ratio equal to 8% equal to that for damping ratio with 5%. And the question is that, is it true for all the cases? In this case, they are equal, but it's true for other cases. And then we move to the modification of the ratio between SAD and FU. From the seismic design code equation 2-2, if the ratio SAD to FU is less than 0.3, no modification. Therefore, the ratio after modification equal to the ratio before modification. If the ratio is larger than 0.8, then it is reduced to 70% of the one before modification. When the ratio between 0.3 and 0.8, SAD divided by FU modification equal to 0.52, SAD divided by FU plus 0.144. And here's the graph, shows the relationship between the ratio before modification and after modification. And then back to the example, the site located at Ruishui Township, Hualien County, with supplemental dampers. The damping ratio of the building is increased to 8%. And the question is find the modification of SAD divided by FU. And from our previous slide, we have already had SAD equal to 0.948 and FU equal to 2.463. And the ratio between SAD and FU equal to 0.3849. And it lies between 0.3 and 0.8. And according to Seismic Design Code equation 2-2, SAD divided by FU modification equal to 0.52 times SAD divided by FU plus 0.144 equal to 0.3441. And then from the previous lecture, we already had the ratio for the damping ratio equal to 5%, and compare this to the modification of the ratio for damping ratio 8% is less than the ratio for the damping ratio equal to 5%. And is this true for all other cases? So far we have the modification of the ratio SAD divided by FU. Once we have the weight of the structure, the importance factor of the structure, first yielding amplification factor of the structure, then we can compute the design basis seismic force according to Seismic Design Code equation 2-3. And then back to the example, and the question is to find design basis seismic force V. What's the value for V? So far we have the information about the importance factor I equal to 1.0, and the first yielding amplification factor alpha Y equal to 1.0, and the total weight of the structure equal to 146.05 ton force. And the multiplication of the ratio between SAD and the FU from the previous line equal to 0.3441. Then, according to Seismic Design Code equation 2-3, V, the design basis seismic force equal to I divided by 1.4 alpha Y, I equal to 1.0, alpha Y equal to 1.0, and the modification of the ratio between SAD and FU equal to 0.3441, and then times W equal to 0.246W equal to 35.9 ton force. And from previous lecture, we have already found the design basis seismic force for the damping ratio equal to 5%. V for the damping ratio equal to 5% equal to 40 tons. And compare these two, and we found that the design basis seismic force for the damping ratio equal to 8% is less than that for the damping ratio equal to 5%. This is true for this case. Is it also true for other cases? Then we move to maximum considered spectral acceleration, SAM, for site class 1, 2, or 3. And according to Seismic Design Code Table 3-2, the maximum considered spectral acceleration for damping ratio other than 5% can be modified by two parameters. One is BS, the other is B1. And after modification, SMS is modified to be SMS divided by BS. SM1 is modified to be SM1 divided by B1. And the corner period, T0 parenthesis M, is modified to be SM1 times BS divided by SMS B1. With the corner period, the relationship can be divided into 4 segments. The first one increases linearly with the structural vibration period T. The second one is a constant spectral acceleration. The third one, it decreases and inversely proportional to the vibration period T. The fourth one is the lower bound for the maximum considered spectral acceleration. And then back to the example, the question is to find the maximum considered spectral acceleration, SAM. What's the value for SAM? From previous lectures about this building, we have SMS equal to 1.32, SM1 equal to 0.869, and from the previous slides of this lecture, we have already had BS equal to 1.198, B1 equal to 1.150. and the structural vibration period of the structure equal to 0.268 seconds. Then from this information, we can compute the corner period between short period and medium to long period. T0 parenthesis m equal to SM1 BS divided by SMS B1 equal to 0.686 seconds. And then compare with the information we get from previous lecture, the corner period equal to 0.658. Therefore, the corner period for the damping ratio equal to 8% is higher than the corner period for the damping ratio equal to 5%. Is it true for other cases? And the structural vibration period, T, equal to 0.268 seconds, and it lies between 0.2 T0M to T0 parenthesis M. Therefore, according to Seismic Design Codes Table 3-2, SAM equal to SMS divided by S divided by BS equal to 1.102. And then compare with what we got from previous lectures, the special maximum considered spectral acceleration for damping ratio equal to 5% equal to 1.32. And then compare this result, and we can have the conclusion that the spectral acceleration, the maximum considered spectral acceleration for damping ratio equal to 8% is less than that for the damping ratio equal to 5%. Is it true? It's true for this case. Is it true for other cases? Then we move to Taipei Basin. According to Seismic Design Codes Table 3-2, if the damping ratio is other than 5%, the maximum considered spectral acceleration for Taipei Basin can be multiplied by two factors. One is BS, the other is B1. With these two damping modification factors, SMS is modified to be SMS divided by BS. The corner period, T0M, is modified to be T0 parenthesis M equal to T0M times BS divided by B1. With this corner period, the relationship between maximum considered spectral acceleration and the structural vibration period T can be divided into 4 segments. Then we move to the maximum considered seismic force reduction factor, FUM. Then according to Seismic Design Codes Equation 2-15, the maximum considered seismic force reduction factor can be computed by two parameters. One is T, fundamental vibration period of the building. The other is RA, the allowable ductility capacity. And with the corner period T0 parenthesis M equal to SM1 BS divided by SMS B1, the relationship can be divided into 4 segments. And then back to the example, the question is to find maximum considered seismic force reduction factor. What's the value for FUM? So far we have some information. T, the structural vibration period, equal to 0.268 seconds. T0 parenthesis M, the corner period, equal to 0.686 seconds. And SAM, the spectral acceleration for damping ratio equal to 8%, equal to 1.102. And R, the ductility capacity of the building, equal to 4.8. And then after comparison, we find that the structural vibration period lies between 0.2 T0 parenthesis M to 0.6 T0 parenthesis M. Then according to the Seismic Design Codes, Equation 2-15, then we can determine FUM, the seismic force reduction factor for maximum considered earthquake. FUM equal to square root of 2R minus 1, and R equal to 4.8. Therefore, we can have FUM equal to 2.933. And then compare with the result we got from previous lectures, the seismic force reduction factor for the structural damping ratio equal to 5% equal to 2.933, and then compare these two values, we can have the seismic force reduction factor for damping ratio equal to 8% equal to that for damping ratio equal to 5%. Is it true? The equality is satisfied in this case. Is it true for other cases? And then we move to the modification of the ratio between SAM and FUM. And according to Seismic Design Code equation 2-16D, if SAM divided by FUM is less than 0.3, no modification is necessary. If the ratio is larger than 0.8, then it is modified to be 70% of the one before modification. And if it lies between 0.3 and 0.8, then we use linear interpolation to connect 2 points. So far we have SAM for the damping ratio 8% equal to 1.102, and FUM for the damping ratio 8% equal to 2.933. And the question is to find the modification of SAM divided by FUM. SAM divided by FUM equal to 0.3757. It lies between 0.3 and 0.8. And according to Seismic Design Code equation 2-16D, SAM divided by FUM modification equal to 0.52 times SAM divided by FUM plus 0.144 equal to 0.3393. And then from the previous lecture, we have the modification of the ratio for damping ratio equal to 5% equal to 0.3780. And then compare these two results. The modification of the ratio for damping ratio equal to 8% is less than the ratio, the modification of the ratio for damping ratio equal to 5%. Is it true for this case? Is this true for other cases? That's the question for all of you. Then from the information we had, we can calculate the maximum considered seismic force Vm. According to Seismic Design Code equation 2-16C, Vm equal to I divided by 1.4 alpha y times SAM divided by FUM modification times W. And then back to the example, the question is to find maximum considered seismic force Vm. What's the value of Vm? So far we have I, the importance factor, equal to 1.00 alpha y, the first yielding amplification factor equal to 1.0, W, the total weight of the structure, equal to 146.05 ton. And from previous line, we have the modification of the ratio between SAM and FUM for damping ratio equal to 8% equal to 0.3393. Then according to Seismic Design Code equation 2-16C, the maximum considered seismic force Vm equal to I equal to 1.0, alpha y equal to 1.0, the modification of the ratio between SAM and FUM equal to 0.3393, and then times W equal to 146.05. Therefore, we can come up with Vm equal to 35.3 ton force. And from previous lecture, we have Vm for the damping ratio 5% equal to 39.4 ton force. Compare these two, then we can have the maximum considered seismic force for the damping ratio equal to 8% is less than that for the damping ratio equal to 5%. It's true for this case. Is it true for other cases? Then we move to small to moderate seismic force for site class 1, 2, or 3. From Seismic Design Codes Equation 2-16a, V star is the small to moderate seismic force equal to I times FUD star divided by 4.2 alpha Y, SAD star divided by FUD star modification, and then times W. And then back to the example. The question is to find small to moderate seismic force V star. From previous lectures, we already have some information. SD star S equal to 0.8, SD star 1 equal to 0.45, BS equal to 1.198, B1 equal to 1.150, and the structural vibration period equal to 0.268 seconds. The total weight of the structure equal to 146.05, and the importance factor of the structure, I equal to 1.00, the first yielding amplification factor equal to 1.0. And then from Seismic Design Codes Table 3-2, we can compute the corner period between short period and medium to long period to T0 parenthesis D star equal to SD star 1 BS divided by SD star S B1, and after the computation we can have the corner period equal to 0.586 seconds, and then we can check the structural vibration period lies between 0.2 T0 parenthesis D star and T0 parenthesis D star. Therefore, according to the Seismic Design Code Table 3-2, SAD star equal to SD star S divided by S equal to 0.8 divided by 1.198 equal to 0.668. And then we check the results from previous lecture. When the damping ratio equal to 5%, SAD star equal to 0.8. Compare these two values, then we can have the small to moderate spectral acceleration for the damping ratio equal to 8% is less than that for the damping ratio equal to 5%. This is true for this case. Is it true for other cases? That's the question for all of you. So far we have the spectral acceleration, small to moderate spectral acceleration equal to 0.668, and the allowable ductility equal to 3.533. And then we check the structural vibration period. It lies between 0.2 T0 parenthesis D star and 0.6 T0 parenthesis D star. Therefore, from the Seismic Design Code Equation 2-15, FUD star equal to square root of 2RA minus 1, and RA equal to 3.533. Therefore, we can have FUD star equal to 2.463. And then compare the result from previous lecture. That's the seismic force reduction factor for the structure with damping ratio equal to 5%, and these two are equal. Therefore, in this case, the seismic force reduction factor for damping ratio equal to 8% equal to that for the damping ratio equal to 5%. This is true for this case. Is it true for other cases? That's the question for all of you. So far we have SAD star and FUD star, and then we can compute the ratio between SAD star and FUD star equal to 0.2712. Is less than 0.3. Then according to the Seismic Design Codes Equation 2-2, no modification is necessary. Therefore, the 1 after modification equal to the 1 before modification. SAD star divided by FUD star modification equal to 0.2712. and then compare the modification of the ratio for damping ratio equal to 5%, compare these two values, then we can have the modification of the ratio for damping ratio equal to 8% is less than that for the damping ratio equal to 5%. This equality is true for this case. Is it true for other cases? That's the question for all of you. So far, we have the multiplication of the ratio equal to 0.2712. We have the total weight of the structure, importance factor of the structure, first yielding amplification factor of the structure. Then, according to the seismic design code, equation 2-16a, then we can have V star, the small to moderate seismic force V star, equal to I equal to 1.0, times FUD star equal to 2.463, divided by 4.2 alpha Y equal to 1.0. And the modification of the ratio between SAD star divided by FUD star equal to 0.2712. And then times W. V star equal to 0.159 W. And after substituting W into this equation, then we can have V star equal to 23.2 ton-force. That's the V star for the damping ratio equal to 8%, and then compare with that for the damping ratio equal to 5% from previous lecture. And we found that the small to moderate seismic force for damping ratio equal to 8% is less than that for damping ratio equal to 5%. Is it true for this case? Is it true for all the cases? For Taipei Basin, the small to moderate seismic force V star, according to seismic design code equation 2-16b, V star equal to I times FUD star divided by 3.5 alpha Y, SAD star divided by FUD star, modification times W, the weight of the structure. So far we have the design basis, seismic force, from equation 2-3, maximum considered seismic force from equation 2-16c, and small to moderate seismic force for site class 1, 2, or 3 from equation 2-16a, or for Taipei Basin from equation 2-16b. Once we have V, the seismic force for the design basis earthquake, and Vm, the seismic force for maximum considered earthquake, and V star, the seismic force for small to moderate earthquake. Among all these three seismic forces, pick up the maximum one and assign it to be the design seismic force for the design of the structures, Vd. Therefore, Vd equal to the maximum of V, Vm, and V star. Then back to the example, the question is to find design seismic force Vd. So far we have V for the damping ratio equal to 8% equal to 35.9 ton-force, and Vm for damping ratio equal to 8% equal to 35.3 ton-force. V star for the damping ratio equal to 8% equal to 23.2 ton-force. And pick up the maximum one, then we can have V star, the design seismic force for the structure, equal to the maximum of V, Vm, and V star, equal to 35.9 ton-force. And here the information obtained from previous lectures. We have V for damping ratio equal to 5% equal to 40 ton-force, Vm for damping ratio equal to 5% equal to 39.4 ton-force, and V star for damping ratio equal to 5% equal to 26.8 ton-force, and then the maximum one equal to 40 ton-force, and then compare this value with the value here, and we find that Vd for damping ratio equal to 8% is less than Vd for damping ratio equal to 5%. Therefore, the higher the damping ratio, the lower the design seismic force. And here's the reference for this lecture, Seismic Design Codes of Building, published in 2011 by the Ministry of Interior. And video for lecture 1 in both English and Chinese versions. Lecture 2, lecture 3, lecture 4, lecture 5, lecture 6, lecture 7, lecture 8, lecture 9, lecture 10, lecture 11, lecture 12, lecture 13, and lecture 14. This is the current one. It is under preparation. And in this lecture, we talk about damping modification for seismic force, including the damping modification for design-based seismic force, for maximum considered seismic force Vm, and for small to moderate seismic force V star. And from these three seismic forces, pick up the maximum and assign it to be the design seismic force Vd. And here's some question for you. The higher the damping ratio, the lower the design-based seismic force. Is it true for all the cases? The higher the damping ratio, the lower the maximum considered seismic force. Is it true for all the cases? The higher the damping ratio, the lower the small to moderate seismic force. And the last one, the higher the damping ratio, the lower the design seismic force Vd. Is it true for all the cases? That's all for this lecture. Thank you. See you next time. Bye-bye.